Hello, in this video we will discuss how the virtual memory mapping takes place between the virtual memory and the RAM. So, essentially let us start with this very famous slide by now, that when you write a program and compile it, you get the executable a.out, and when you execute this particular executable a.out executable, the operating system will create a process for you. Now, the process is represented by what is known as the virtual address space. Now, the virtual address space is a contiguous address space starting from 0 and extending up to an address defined by something known as a max size. This max size comes from the Xv6 nomenclature. Now, within this contiguous virtual address space for the process are various sections like the text, data, heap and the stack. So, all these sections are created by the operating system. Essentially, the operating system will need to know where the heap would start, where the stack would start and so on. So, how does the operating system know all these information? So, this information is given to the OS through the a.out. Essentially, what happens is that when the program is compiled and linked, the compiler will put a lot of these information in the executable a.out. So, when executed, the operating system will read out this information and then determine where in the virtual address space should these various segments be present. So, now when this process is executing, all these instructions corresponding to printf for instance gets executed, and all addresses corresponding to str is accessed. So, it may be noted that all these addresses, all these instructions would be mapped into this particular virtual address space. For instance, if I were to print the address of hello world, essentially the address of this str, then the result would be the virtual address with respect to this particular mapping. So, what we will next see is how this virtual address map gets mapped into the main memory of the system. So, let us say that the processor wants to access this particular string, at least the base address of this string, and as we know that would contain the letter H. So, what would happen is that the processor will put out a virtual address on its bus. So, let us say this virtual address is V, and this virtual address could be in the range from 0 to max size. So, max size is the largest address that a user space process could have in its virtual address space. So, said another way, the virtual address V would be some address in the virtual address space of the process. Next, another unit in the CPU known as the MMU or the memory management unit. So, this entire thing would typically be in the same package or jointly called the CPU or processor, would then take the virtual address and convert it to a physical address P, which would then be used to access the RAM. So, what we will see next is how this virtual address gets converted to the corresponding physical address. So, it may be noted that the virtual address corresponds to the virtual address map, but the physical address corresponds to one physical address in the main memory or the RAM. So, when a process begins to execute, the operating system would create a page table for that process in RAM. So, this is the page table, and as we have seen in the previous video, the page table holds the mapping from the virtual blocks or the virtual address space of the process to the physical page frames, and we have other bits like the present bit, dirty bit and the protected bit, which is not shown here. Now, in the memory management unit, there is a register known as the page table pointer register or PTPR. So, in the Intel systems, this PTPR or page table pointer register is known as the CR3 register, and we will see more details of this in a future video. So, this PTPR register present in the MMU will have a pointer to the process page table. So, let us see how these things are used to provide the mapping from the virtual address space to the physical space. So, what happens is that the virtual address which is sent out by the processor core comprises of two parts. It has a table index, which are the a few bits of typically the most significant bits of the address, and an offset. So, when the MMU obtains this virtual address, it is going to look up the process page table corresponding to the offset present in the table index. So, the PTPR would be the base address of this particular process page table, and the higher bits in the virtual address would correspond to the offset in the process page table. So, from here the corresponding page frame is taken and it forms part of the physical address. Now, the second part of the physical address is directly taken from the offset. So, in this way we would then create what is known as the physical address, and it is this physical address that is used to access or to address the RAM or the main memory. So, let us see how this MMU mapping works for a 32-bit system. So, in a 32-bit processor, the virtual address space could be at most 2 power 32, that is 4 gigabytes. The virtual address is of 32 bits as shown over here, and this is typically divided into two parts, the table index and the offset, which is of 20 bits and 12 bits respectively. So, how did we get this particular thing is by the fact that each page frame, as we had mentioned in the earlier video, is of size 4 kilobytes. Thus, to access any offset within the page frame would require 12 bits, because 2 power 12 is 4096, which is 4 kilobytes, and therefore, we have an offset which is of 12 bits, which essentially would give the offset within a page. The remaining bits, that is 32 minus 12, which is the 20 bits, would be used for the table index. Thus, the process page table would be, which is indexed by this 20 bits, would have 2 power 20 entries. Now, assuming that each entry is of 4 bytes, then the entire size of this page table is 4 megabytes, and what essentially is required is that this page table has to be contiguous. That is, we need to have these 4 MB of process page table to be in contiguous memory locations. So, why do we need it to be contiguous? Is essentially that the table index is added to the process page table pointer in order to get the location of a particular block and the corresponding page frame, and therefore, it needs to be in contiguous memory. Thus, we see that each process that executes on the system will have the additional overhead of having a 4 megabyte process page table. While 4 MB is not a very large space with today's RAM sizes of 32 and 64 gigabytes. However, the requirement that it needs to be contiguous would be an issue. So, what some systems do, especially the Intel systems, is to have two level page translation. Essentially, instead of having just a table and offset for the virtual address, now we have three components in the virtual address. We have a directory entry which is of 10 bits, a table entry which is also of 10 bits, and the offset which as usual is of 12 bits. Now, corresponding to the virtual address, what would happen is that the directory entry is used to index into something known as a page directory. Now, this page directory is pointed to by the page directory pointer register present in the MMU. Now, the contents of this entry in the page directory would point to a particular page table. So, this page table is of 4 kilobytes and this is also of 4 kilobytes, that is the directory is also of 4 kilobytes. Next, the table entry is used to index into this particular 4 kilobyte table, and from there we obtain the first part of the physical address, and as usual the second part of the physical address is taken from the offset. So, how does this scheme actually help us? Now, what we see is that the number of page tables that can be present, that is number of these, is 2 power 10 or 1024. And how do we get 1024? Is that we have a 10 bit directory entry over here and 2 power 10 is 1024. Thus, the directory page table is of 4 kilobytes having 1024 entries or 2 power 10 entries. Since each entry points to a different table, thus we can have at most 2 power 10 different page tables. Each entry in the directory would point to a different page table. Now, how is the scheme actually helping us? So, in total, although we still have 4 megabytes of page tables that is required, but the advantage we get is that they are not contiguous. So, we just need to have chunks of 4 kilobytes which needs to be contiguous, and this is easily obtained because each frame in the RAM is of 4 kilobytes. So, the two level page translation would allow us to have non-contiguous page tables present. Next, we will look at the sequence of steps that occur during the virtual memory mapping. So, let us start with the particular program, and this is its virtual address space with different colors corresponding to each section of the program. Also, we have the various blocks, and as we have mentioned, each of these blocks is of 4 kilobytes. Then what we have seen is that also there is a process page table present in the RAM, and there is the RAM itself, which is again split into equal size blocks known as the page frames. Now, there are actually 3 entities which are involved with the working of the virtual memory. That is the operating system, which is the software component of this, while the processor and the MMU, the memory management unit, are the hardware components. So, let us say that we have started to execute this program, and this particular line in the program is the first instruction being executed. Now, let us see what is the sequence of steps that occur as the program executes. So, essentially when the user runs this particular program, it triggers the operating system to create this particular process page table in RAM. So, ideally this particular page table will have the present bits set to all 0, and the other parts of the page table may or may not be empty at this particular point in time. Third, the RAM may or may not contain any of the process blocks corresponding to the newly created process. Next, what happens is that the operating system would transfer control into the main function of the program. So, this main function in the C code would probably point to a particular instruction in the virtual address space. So, this would result in the processor sending a particular virtual address corresponding to the main function. So, this virtual address would be sent onto the bus, and this virtual address is then intercepted by the memory management unit, and the MMU would then look into the page table of the process and determine that that corresponding page or that corresponding block is not present in the RAM. So, this is determined by the 0 bit present in this particular bit. So, that is determined by a 0 in the present bit. So, as a result of this, what the MMU is going to do is that it is going to cause a page fault to occur. So, when a page fault occurs, it is going to trigger the operating system to execute. So, then the operating system is going to execute and determine the cause of the page fault. So, essentially there is a sequence of steps that the operating system does whenever it whenever the page fault occurs. So, these are that it will first check if the page referred is legal, and only if it is legal it will continue. Then it will identify the page location on the disk corresponding to this particular block. Then it will identify a page frame to in the RAM that will need to be used. Then essentially if it requires that a swap out process is needed, and if the dirty bit is set, then the page which was previously present in the RAM would be written back into the swap space, while this is followed by the block corresponding to this virtual address being accessed loaded from the disk into the RAM. So, this essentially is done by what is known as a DMA transfer from the hard disk to the RAM, and the operating system would just need to trigger this particular DMA transfer to be initiated, and also it is going to update the page table. So, essentially it is going to say that the first of all the present bit is set to 1 and the page frame corresponding to block number 2 will be set to 11. Then after the page gets loaded into RAM, the transfer comes back to the CPU or the processor, and the processor would reissue the instruction. So, this instruction would mean that there is a virtual address being sent on the processor bus, and it would cause the MMU to convert that virtual address into the corresponding physical address. So, now what the MMU is going to see is that it is going to look into the process page table, it is going to see that the present bit is set to 1, therefore, it would mean that the block is loaded into a page frame in the RAM, and it would then be able to convert the virtual address to the physical address and cause the instruction to be loaded from the RAM into the processor, and in this way the processor executes an instruction. Okay. So, this is the sequence of steps that occur with the virtual addressing scheme. Essentially it not only involves just the operating system, but there is a interworking between the operating system, the processor and the memory management unit in order to achieve virtual memory. In other words, in order to make the virtual memory begin to work. Thank you.